Okay, so based on the ideas that we established in the two previous videos, we now introduce the equation of straight lines in 3D space. So we're going to consider a line in the XYZ frame, which goes through a point P naught with coordinates x naught, y naught, z naught. Point P is going to be an arbitrary point on the straight line with coordinates x, y, z. So the equation of this line, so the equation of a straight line which passes through x naught, y naught, z naught, and let's say it has got a direction vector, so imagine the direction vector is given by alpha, beta, gamma, which we can write like this or like that. So the equation is going to be, the vector equation is going to be given by exactly the same equation that we established for a straight line in 2D. So it's going to be xyz, which is position vector of the point xyz, equal to the position vector of p naught, x naught, y naught, z naught, plus t, which is going to be a parameter, times the direction vector. Okay, so in compact form, this is equal to r, this is r equals r naught plus t, which is a scalar parameter, multiplied by the direction vector m. So this is the vector form of the equation of the straight line in 3D. Again, if we take the individual components, x going to be x naught plus alpha times t, or t times alpha. Okay, so it's going to be x naught, x is x naught plus alpha t, y is going to be y naught beta t, z is going to be z naught plus gamma t. This is the parametric form. Okay, you're going to notice that the form exactly the same as we established for 2D. And then the symmetric form, x minus x naught over alpha is t from the first equation, y minus y naught over beta is t from the second equation, z minus z naught over gamma is t from the third equation. This is the symmetric form. Okay, and you can see that they are, well, exactly the same form as we established for 2D. So like we mentioned, when you have got equations in vector form, when you go from 2D to 3D, the form of the equation remains exactly the same. All you do is you inherit a third component in your vectors, which is the z component. The other thing to note is that for lines in 3D, there is no corresponding form of the equation of a straight line which looks like this. Okay, so y equals mx plus c will not have anything that looks like it. It's only going to be your vector form, your parametric form, and your symmetric form for lines in 3D. Okay, so let's look at a few examples. Okay, in this example we have got two lines. We have got L1, which is a line that passes through the point 4 minus 3, 5, and it's parallel to the vector 5, 1, minus 6. L2 passes through the point 1 minus 3 minus 2 and 2, 3 minus 9. In part A, we want to find the vector, the parametric, and the symmetric form of each of these. In part B, we want to find the angle between L1 and L2. In part C, we want to find the intercepts of L1 with the coordinate planes. Okay, so let's see how this works out. So let's start with L1. So for L1 we have okay, so for L1 we have got a line passing through 4 minus 3, 5, and parallel to the vector 5, 1, minus 6. So this automatically gives us our x naught, y naught, and z naught, because that point is on the line. So that means straight away we can write x, y, z is equal to the position vector 4 minus 3, 5. Then for the direction vector, since the line is parallel to this vector here, that provides us with the direction vector 5, 1, minus 6, and there you are. That is the vector form of the straight line L1. Then the parametric form, if we break this down into the individual components, x is going to be 4 plus 5t, y is going to be minus 3 plus t, z is going to be 5 minus 6t. That is going to be your parametric form. Okay, then if you make t the subject of the formula in the x component equation, then we got x minus 4 over 5. In the second equation, we got y plus 3 over 1. And the third equation, we got 5 minus z over 6. And so that's going to be the symmetric form of the equation. Then we want to do the same thing with L2. So L2 is a straight line that passes through 2 points. So if I just make a rough sketch of this line, minus 2, 2, 3, minus 9, then we could use any of these as x0, y0, z0, but we need the direction vector. But the direction vector we can get by subtracting one of these from the other. So our direction vector, for instance, if we do this point minus this point, it's going to be 2 minus 1, 3 minus negative 3 is going to be 6, then negative 9 minus negative 2 going to be negative 7. If you do this the other way around, then it's simply going to be negative 1, negative 6, and 7, and that's completely acceptable. So the vector form of the equation is going to be, you can either use the position vector of this point or this point. Either of them will be acceptable. And then the direction vector 1, 6 minus 7, or negative 1, negative 6, positive 7. And then of course t here must be a real quantity. Break this into the individual components. X is 1 plus t, y is negative 3 plus 6t, z is negative 2 minus 7t. That is the parametric form. Then make t the subject of the formula in each equation. The first equation, t is x minus 1. The second equation, t is going to be y plus 3 over 6. The third equation, z is going to be minus 2 minus z over 7. And so that's going to be the symmetric form for L2. In part B, we want the angle between L1 and L2. So here what we need to do is to recall the direction vector for M1, which was 5, 1 minus 6. Direction 5 minus 1, 6. That's the direction vector for L1. Direction vector for L2, just did a second ago, 1, 6 minus 7, 1, 6 minus 7. And so the angle between these two lines is simply going to be the angle between the direction vectors. So using the dot product, m1 dot m2 is going to be the magnitude of m1 times the magnitude of m2 times the cosine of the angle between these two. So m1 dot m2 is going to be 5 minus 6 minus 42. So 5 minus 6 minus 42 is minus 43. So minus 43 here. The magnitude of m1 is going to be 5 squared, which is 25. 26 plus 36. 26 plus 36 is 62. So we want the square root of that. Then the magnitude of M2 is going to be 36 plus 49. 36 plus 50 sounds like 86 cosine theta. So theta is going to be the inverse cosine of negative 43 over square root 62 times square root 86. Now, since the cosine of this is negative, it tells us that the angle between these two is not going to be acute. It's going to be obtuse. So let's see what that works out to. So inverse cosine, first make sure we are in degrees. Inverse cosine 43 negative divided by the square root of it's 62 and 86. 62 times 86. Okay, we have a problem obviously because we did the cosine, not the inverse cosine. So let's do the inverse cosine. Inverse cosine 43 negative divided by the square root of 62, not 32, times 86, not 56. Let me see. Yes, 86 is correct now. 126 is going to be the angle between these two vectors. It's in degrees. So that means the vectors, or these lines, are going to be have that type of orientation. All right, so there is example number B. Example number C, find the intercepts of L1 with the coordinate planes. Intercepts of L1 with the coordinate planes. We have got 3 forms of equation here. The best form to do this will be I'm still trying to decide. Let's try the symmetric. Let's try the symmetric and see how that works out. That doesn't work out nicely. We'll go back to the parametric. So example number C. The symmetric is this one here. So with the coordinate planes, there are 3 of them. So there is this one here, which is going to be the XZ plane. Then there is this one, which is the XY, and then there is going to be this one, which is going to be the YZ plane. So let's start with the XY plane. Along the XY plane, Z is equal to 0. So along the XY plane, Z is equals to 0. X and Y vary. So Z equals to 0. So we're going to have to plug in Z equals to 0 there. and then you can get y, you can get x. Okay, so if we plug in z equals to 0, here there's going to be 5/6. So for y, it's going to be y plus 3 is 5/6. So y is going to be 5/6 minus 3. So that's going to be 5 minus 18 is so it's going to be minus 13/6. Okay, then for the x, going to be x minus 4/5 is equals to 5/6. X minus 4/5 is 5/6. So x is going to be 4 plus 25/6. That's going to be 24 plus 25. So that's going to be 49/6. So that means the intercept with the xy plane is going to be 49/6. Y is minus 13/6, and z is 0. And then you can do the same thing or something similar with the xz and the yz planes. Right, we're going to do example number 2 in the next video.